Okay, continue. Okay, so anyway, so we will do our teaching for this session. Okay, so I show my face on the left hand corner. It will get blocked anyway. Okay. So today we are going to talk on a new topic, right? So you go to the course. So there are two files I just uploaded about maybe like last night, like 3 o'clock or 2 o'clock. So it's a lecture that I have prepared, one of the few last lecture on this thing called Rayleigh algorithm. So there are two files. One is a Rayleigh algorithm file, which is shown here, like this one. Okay, so you can click on it, or you can run it online, or you can download it, and then the same link would link to another file, which is a PowerPoint file. Now this PowerPoint file has a simulation. You can't see the simulations because sometimes if the line is low, you can't. So you may want to download the PowerPoint file into your laptop, and then this is the PowerPoint file that I'm talking about. Okay, this is not the PowerPoint file. This is a PowerPoint file for the assignment. Okay, there's another PowerPoint file which I will show you. This is the lecture notes. Okay. Okay, so this is not the one that I'm talking about. The PowerPoint file, yeah, this is the one. Okay, so it has a simulations finally to show you that we're going to simulate something which is really like more advanced and more interesting. I would say that the topic that we're going to discuss today is one that is more interesting, okay, than the one that we are simulating. So we are still on a simulation, but these simulations is not really solving differential equations or solving equations like in other cases. So in the previous case, when we talk about the simulations, we have a set of differential equations, then we solve it, right? But this is slightly different. This case, it's we solve the Newton's law. You specify the force acting on the Newton's law, and you specify the force acting on. Okay, fine. Someone no sorry. This is not good. So let me shut off these things. Okay. So. Now we are still on a simulations using the Rayleigh algorithm. So in this Rayleigh algorithm, what you do is that you are giving a force acting on the particles. Then the force will cause the particles to draw a locus, I mean the trajectory. It's just like typical case would be a pendulum. So a pendulum is subjected to a force. So you know what is the forces that acts on the pendulum. For a pendulum that move in 2 dimensions, you have two forces. Like one is the force that acts along the radial directions, another is on the tangential direction. For the more familiar case is the projectile motion. For projectile motion, you have one force acting on the projectile, which is the gravitational force pulling downwards. Then along the horizontal line, you have the force along the x direction. What is that? The force for a projectile motion along the x direction is 0. Okay, so you know exactly what is the forces acting on the particle at any instant of time. Now, theoretically, if you know what is the forces that acts on a particle, then the force actually causes the particle to accelerate. If you know what is the force of the particle, you would know how the acceleration of the particle is. Like the force is the cause for the change in the motion. So you use force to describe the physical reasons of the physical cause for something to change in its state of motion. So that is one side. Force is one agent that causes a change in the state of the motion. Then the state of the motion, on another hand, is not force. It is just a mathematical descriptions of how the locations of the object change with time, how the velocity of the object change with time, and what is the accelerations of the object that is subjected to the force. So the force, like in this case, on the screens, you can see me, I suppose. On the screen, the F on the right hand side is the cause for a change in the state of motion, and then on the left hand side, which is d to r dt square, refers to the change of the state of motion. So this is the accelerations, and accelerations is closely related to the velocity and also related to the instantaneous positions. Okay, so if you know the force, you should be able to deduce what is the accelerations of the particles, and from acceleration you can deduce what is the velocity, and then from there you would be able to deduce what is the position at any instant of time. Okay, so assuming that you know the initial velocity, the initial positions of the particles, then you'll be able to calculate at any instant of time, t1, t2, t3, t4, t5, t6, whatever, from t0 up to also a large amount of time steps later. At every time step, you are able to know where exactly the location of the particle is and the velocity of that particles at any instant of time. So if you know the positions of it at any instant of time, t1, t2, t3, then you can display the positions of the particles as a point on the xy plane or xyz plane. If we are talking about three-dimensional motions, then you'll be seeing a point of particles that will trace out some kind of trajectory in the form of a video. Right? So this is what we are going to do. If you think about it slightly, this is slightly different than the simulation that we did previously. But in the simulation that we did previously, involves generating the point by looking at the numerical solutions for the differential equation. So for example, in your assignment, you know what is the formula for the planetary motions, right? So you know how the you know how the radius and position change with time. So that information of how the position change with time is given to you in the form of a formula, but there's no force, right? The force is actually been calculated already. So the result of the trajectory, which is coming from the force acting on the particles, is translated into the form of its orbit. Okay, so the force on the planetary motions has to be written down in some kind of in the assignment you have done more complicated things than that. So you have a differential equation involving the force of r dot dot and theta dot dot and things like that, right? Then you solve this r dot dot and theta dot dot into r dot and theta dot, and from there you got this r and theta as a function of time. So from there you plot out the points of the instantaneous locations of this planet. Then you displace their instantaneous location from time to time. Then you have this video, right? So in that process, you need to solve a second order differential equations. Okay, so you see the line here. So previously we solved the second order differential equation using RK2. RK2 here is just the algorithm that you use in your Python to solve the differential equation. I'm not sure whether it's RK2 or not, but well, it is an algorithm that is used to solve differential equations anyway. So Okay, maybe the Python code that you use is not using RK2, it's using some other algorithm. But anyway, this is different than the previous one in the sense that you give me what is the force of the particles, and then from the force of the particles, you calculate the accelerations, and then from the accelerations, you're able to calculate the instantaneous positions and the instantaneous velocity. So it is like this. You always know the force acting on the particles in real life, right? So for example, a pendulum, you always know at what location what is the force acting on it. So most likely, in most cases, you would think about it, particles that are subjected to a force only depends, okay, think about it, only depends on the position, but never or seldom that you see a force dependent on its velocity. Okay, I think this is quite a generic features in physics. Okay, so the pendulum's force on the pendulum does not depend on its velocity, but only depend on the position. Remember the pendulum, the force is what is F equals to minus kx, right? So the x is the positions. So the force or acceleration force of this pendulum is dependent on the velocity, on the position. So if you know the position, then you can calculate the force quite easily. Okay. So once you know the force at any locations, you can in principle calculate the positions. From the force, you can calculate the accelerations, and then from the acceleration, you can calculate the velocity and also the positions. Okay, but the details of the derivations for this, for the Malay algorithm can be found from the link. So I set a link. So this is the derivations which we are not going to talk about in detail. It's about physics. So in principle, you tell me what is the acceleration. Then from there, you derive the locations as well as the instantaneous velocity. So these are the derivations of the formula. It's not that difficult. So you go through all these details, and finally you come up with this set of equations. That is this. Okay. So it's algorithm, meaning that it's a step-by-step procedure which you can follow and write into a code form, and then from there, this code will tells you the positions. So this is the positions of any particles at the next time step. So if you know, for example, on the right hand side, you look at this one. On the right hand side, you know, for example, at the present moment, at time t, what is the accelerations, and at the moment of t, you also know what is the velocity of the particles, and at the same moment of t, you also know what is the position of the particle. Right? So initially, for example, you know what is the v, what is the a, and what is the t of the particles. Then this formula says that you can calculate the positions of the particle at the next moment, t plus delta t. After some time, delta t later, what is the location of the particles? Okay, so if you look at the right hand side, the x and v is just the kinematic information that is provided in the beginning. You know what is x naught, you know what is t naught. Now there's this accelerations. This acceleration is calculating from the knowledge of the force that acts on the particle, right? So this A is calculated based on the force, the formula based on what force are acting. So if you are talking about a system where the force is coming from tension, like coming from say the gravity, that force will give you the accelerations. If you talk about a two-dimensional projectile motion, then this force of gravity will give rise to the accelerations. Okay, so just be aware that the acceleration that you see in a Malay algorithm is closely related to what kind of force acting on the particles. And in different systems, the force will act differently. For example, I mentioned already to you the case of a 2D projectile motion. I mentioned to you a pendulum motion. What else can you think of a force acting on a system? Okay, for example, you learned about 102. In 102, you learn the electromagnetic interactions. You have a charge going into an electric field. Right? So then the charge will interact with the electric field through the Coulomb force. Right? So in that case of electric field, you have a Coulomb force F. Right? This Coulomb force depends on the distance between two charges, and this Coulomb force will give rise to the accelerations. Okay. Then another case would be, say you have a object, a charge again, that is interacting with a magnetic field instead of electric field. A charge can interact with an electric field. A charge can also interact with a magnetic field if the charge is moving. So you talk about charge that is moving in an electric field. What do you have? You know what is it? You remember what you learned in your physics? If you have an magnetic field going in some directions, when the charge go in, then you have to use the right-hand rule. You have to use the right-hand rule to calculate the force, the so-called Lorentz force, acting on the charge when it goes into the magnetic field. And that Lorentz force will cause the charge to go around. Right? So these are all the basic physics you learn in 102, the basic physics you have learned in your secondary school, from 6 again. So I'm just reminding you that you have seen many different types of forces. Lorentz force, magnetic force, that's called magnetic force. You have electric force, or called Coulomb force, and you have Newton's force, like those mechanical forces coming from gravity, coming from spring, and there are many other types of forces as well. So every type of force, if you know a formula of that force, then that force will be translated into the acceleration. Okay, so you find out that in my 101, I always tell you that this is what you learn in your past, this is what you learn in your past, because we are going to make use of this example to do our summation. Okay, so now once you know that force at time t, the velocity and x, then you can calculate the position of next positions in the next time step. Now, once you have calculated the position of that time step, then you can calculate again the accelerations in the next time steps. So how do you calculate the acceleration from next time steps? Now, this is very simple because you know that the force is always the acceleration is always coming from the force, and you know the formula that relates the force and acceleration. So you are given a formula. For example, in the case of a pendulum, the force is just minus kx. Right? So you always can calculate the force at any instant of time, whether it is in this moment or in the next moment. So you use the force formula to tell you what is acceleration in the next moment of t. So t plus delta t means next moment. Okay, so at the present moment is t, next moment is t plus delta t. So then you derive the acceleration from the force. The interaction potential here means the force. Okay, the interaction potential means it's the force formula F equals to ma. Then from there, you have able to calculate the force. Then from that force, so where am I? Okay, sorry. Let me say it again. Once you know what is the position at the next moment of time, then you also know what is the formula for the force and the accelerations. Now, so the moment the accelerations in the next moment of time is dependent on the force formula, like F equals to ma, such as minus F equals to minus kx. And you also need to know the information of the positions of the particles at the next instant of time. So in order to know the accelerations in the next moment, you need to know not only the formula for the force and acceleration, you also need to know the positions of that particle in next moment. And this information of the position of the particle in the next moment is calculated from step number 1. Okay, step number 1 gives you this information. Then in the second step, you use the information that calculated from step 1 in addition to the formula of F. Then you'll be able to calculate the acceleration in the next moment. So this is in the future, okay? So the present is t, the future is t plus delta t. So you know x at next step, a at next step after 2. Now, so using the information from x at the next step, a at the next step, Then you go to the third step. The third step is to calculate the velocity in the next steps. Right? So in the process of doing the simulation, you need to know accelerations, position, and velocity. Okay, so 1 and 2 give you the position next step, and acceleration next steps. After you have calculated these two, then you go to calculate the velocity in the next steps. And the velocity of next steps is dependent on the present velocity v at t plus the average. Okay, a plus a at t1 means that average of the acceleration made up of the acceleration in the previous step and next steps. Okay, so a is acceleration that has already been calculated in the beginning, and then this is the a at the next steps, which is coming from the second steps. So you add them up, you divide by 2, then that will give you the average of the acceleration between this moment and the next time step, multiply with a delta t. So delta t is the gap in the time step, right? So that would then give you the velocity in the next time steps. So you start off with x at t0, a at t0, and v at t0. That is the information that you know. And from there, you calculate x at 1 delta t, a at 1 delta t, and v at 1 delta t. Then you proceed to calculate x at 2 delta t. Right, so you go back again. So if you know what is this v at 1 delta t, then this information will then be fed back to the to be used to calculate x in the next time step. So in the beginning, x is calculated for x plus 1 delta t. Then after you have obtained this one, you go back again, then you calculate x at 2 delta t. Then you calculate a at 2 delta t, v at 2 delta t. And then given the v at 2 delta t, then you go back to calculate x at 3 delta t. So you write a for loop to iterate the time steps. In each iterations, you calculate x at next moment, v next moment, a next moment. After this, then you go back again, calculate x at next moment, a next moment, v next moment. So by doing that, you'll be able to generate the locations of the particles step by steps. Then you'll be able to display it and do a simulation. So the idea is actually quite simple. So this is just to tell you that Rayleigh algorithm is very stable to perform this kind of equation. So the second order differential equation sometimes can be not very stable. Now we don't really talk about this in detail. It's about the numerical stability. So if you have second order differential equations or a differential or ordinary differential equation or whatever equations, you have to have a numerical code to solve it. Some numerical algorithm, we don't really talk about the details here. Last time we used to ask you to write a code to calculate, say, the Runge-Kutta second order differential equation method or no integration method. But each method has to be written down by using our code instead of calling the Python packages. Right? So when you differentiate or you integrate, in the previous case, in my class, I teach you the Python package that allows you to use it. But in actual fact, last time, not only we use the packages, but we also write the package. You write the algorithm for integration, not calling the package, but write a code to perform integration. And then we also write the code to solve a second order differential equation itself, using the Python solver. So different types of algorithm has different stability. Some is very stable, some is not so stable. Stable means that errors will get accumulated and sometimes it doesn't give you the correct answer. But Rayleigh algorithm is very stable because the error is well controlled. I think it's proportional to delta t squared. So if you have a better algorithm, then the proportionality here means is delta t will be larger. Right? So the larger is of this proportionality, delta t power 1 is less better than order of delta t squared. I mean, if you have a larger delta t error, that means it's better, right? So that means you can tolerate much larger error. So because you set your delta t, the delta t is smaller, and when you square it becomes even more smaller. But if you have an error that is delta t power 4, that means it's very small compared to delta t which is power 2. Right? So it turns out that the Rayleigh algorithm has error order of power 2. Some other mechanisms or some other algorithms have only delta power 1. Right? So that makes it quite stable. So for solving numerical methods, we always talk about this error in order of power 2 or power 3. Okay? Okay. So this is just a numerical mention about the numerical stability. Okay, so let us look at this example. This is a very simple example where you have a let us look about you have a very simple case. You have a one-dimensional problem, simple harmonic oscillator. You want to find out what is the positions and the velocity given you have a mass of a constant, right? So this is just a formula. This is slightly different than the pendulum. Like even the pendulum is a 1D pendulum. Now as oscillates under the gravitational force, and that pendulum is following the similar formula. Okay, that is the period is dependent on L over G. But in the case of a spring, right, the spring is also a simple harmonic oscillator. So that in this case, the K here refers to the spring. So we're talking about a spring that has a constant of K. Then the force of the spring is inversely proportional to the displacement. So the X is the displacement. So these are all the things that you have familiar. Okay, so instead of F equals to minus mg, sorry, in the case of a pendulum, the force is equals to, I think, minus whatever theta. F is proportional to minus theta. Okay, in some approximation. So here it's very similar with the pendulum. We talk about a spring having a constant of k. Then the accelerations is just minus k over m. So k here refers to the spring constant. So larger or the harder is the spring, then the force is larger when you displace it. And x is the displacement, the equivalent position. So this is a Newton's law. You just apply blindly the Newton's law onto a spring. Then you got this form of formula that express the accelerations of the pendulum in terms of the displacement from the equivalent position and the constant of the mass of the object, say 1 kilogram or 100 grams, and k is a spring constant, say 1 Newton per meter or something like that. Okay, so this is the Newton's law for a spring. So we are going to use these situations for the spring to calculate the instantaneous locations of the particles and simulate it. Okay, so how are you going to do that? So in the case of this Rayleigh algorithm, what you need is that you need to know what is the force, and from the force you translate into acceleration, and then once you know the acceleration, then you can calculate the positions, velocity, position, acceleration, and the velocity using this method. So what you need is just like this is the left hand side on this is just a formula. I just cut here to show you this is the Rayleigh algorithm. So how are you going to translate the Rayleigh algorithm into a step-by-step formula? So this is how you do it. So initially you assume that you know the positions of the particles at time 0, and it says 0.1. So this is a case where you have a spring, you displace it by positive 0.1 meter, and then you set the mass to be 1 kilogram, and then k to be 1 Newton per meter, and then you release it. When you release it from rest. So you have two initial conditions, right? The velocity here, the velocity, and also the initial velocity and initial positions. So then you can also write down the frequency omega in terms of k over m. Then you calculate the period of the oscillation in terms of 2 pi over omega. Okay, so these are all 103, right? Your pendulum. You must know your pendulum at your fingertips. We have been using it again and again. So pendulum is a very classical example which we keep on using because it appears everywhere in physics. So when you do simulation, you always use pendulum as a template to illustrate some idea. So a pendulum has the restoration force, Newton's law, and then its solution is periodic. Then you must know what is the periodic, what is the frequency. The frequency is dependent on the physical strength of the spring, and then it's also dependent on the mass, right? Okay? So these are all known. Now once you have known the period of the pendulum, then you say, okay, now I'm going to do a simulation. Then you have to express then your simulation in terms of how many period you want to do it. Okay, so you said I'm going to simulate for 1 period. So then you said 1 period is a 2.5 seconds or 10 seconds. then you decide that you're going to simulate how many snapshots within this one period. So the snapshots, time between two snapshots, is the resolution in time, delta t. So this resolution of delta t is just expressed as the total time you want to do a simulation divided by some constant. So you have to choose a constant, 100, 200, whatever. Now once delta t is chosen, then you start to do the translation. Translation means that you translate the Newton law into the Boole algorithm on the left hand side of the slide. So initially you know what is your A at time t, and this is related to minus k over m equals to xt. Right? So this is the first line you start out with. The Newton law tell you that the velocity at time t and the position at time t is just related by these constant equations. Very simple. Okay, so once you have applied the Newton law to write down the relationship between the acceleration and the positions, then you would start the translation process. Just try to express x at the next step. So the x at the next step, assuming that you know what is the x at the present step, so the t will in the beginning start from 0, okay? Then the t will keep on stepping. Okay, so once you know the initial values of x and ax at t, then the x at the next moment of t, according to the left hand side here, is just expressed as the values of x at t plus v at time t multiplied with the delta t is a constant, plus the product of a at time t times delta t squared. Okay, so this will tell you now what is your x at the next moment. Now once you calculate the x at the next moment, then you calculate the a at the next moment. Now what is the a at the next moment? A at the next moment is simply given by the Newton's law. A is equals to some constant times the positions. So if a at t plus delta t, then a at t plus delta is just related to x at t plus delta t. So easily you write down this line of law of equations. Ax at the next moment of time is just expressed as the informations of x at the next moment. So this a at the next moment that you look at follow my mouse here, is already calculated in the previous steps. Right? So in this step, you calculate x at t plus delta t, and this information will be used on the right hand side of this equation to tell you what is the values of a at the next moment t plus delta t. Now once the a at next delta t is calculated in the second step, then you go to calculate the velocity in the next steps. So what is the velocity in the next step? The velocity in the next steps is just equals to this formula here. The velocity in the previous steps, v at t, plus the average of a in the previous steps, and the acceleration at the next steps, then multiply with delta t. So these are the equations that you're going to write down to do your simulation. So this is just to show you another way of doing the comparison. So you calculate the x at the next moment, and the a at the next moment, v at the next moment. So in the Python code, this is what you write. Initially, on the right hand side is a Python code, okay? So you know what is your x at 0 time, v at 0 time, then you fix what is your delta t, then you write a loop. Right? So you write a loop to loop a constant n from 0 to nt. Now you have many time steps. You say nt is 100 or 1000, whatever. So for every values of n labeled by the integer n, then the time is just the number n times delta t. So when n is 0, it means in the beginning. Right? So in the beginning, and n is 0, then you have to know what is your x at 0 and v at 0. So this is the initial condition that you must provide in the beginning. Now once you step into the for loop, n takes the values of 0 in the beginning. Right? So when you go into the loop, t at 0 is calculated to be 0. Ax at 0, n is just equals to x at 0. So a at 0 and is equals to x0 will be calculated. So ax will be known because you provide the values of x at 0. Right? So x at 0 serves as the initial condition. When it goes in the loop, then first you calculate x at 0, then that will give you a at 0. Once a at 0 is calculated, then you proceed to calculate x at the next steps. Right? X at n equals to 1. X x at n equals to 1. So when you go into here, n takes on 0 in the beginning. So you calculate x at next steps. It just equals to the previous x plus this expression. So we are going to look at this x at n plus 1, a at n plus 1, and calculate v at n plus 1. Then this whole loop will repeat for n equals to 0, n equals to 1, n equals to 2. As I think there's an error here. It's not a 0. I think it should be 0, 1, 2, etc. Okay, so I think there's a slight error. So okay, I'm going to save this, and then it should be synced to your lecture notes. Okay, so that is for projectile motion. So now just translate this into a simple Python code. Now once you have done that for 1D, then you go to the simulations for the 2D code, and then you go to once you know how to simulate the 2D code, then you go to do your assignment. Okay, so in this case the situation is slightly more complicated, but not that much complicated. For 2D, you have to simulate the Worley algorithm for the x direction as well as the y direction. So you have to simulate two components independently. So in the two-dimensional motions, you have to understand that you have two-dimensional motion. One is along the x direction, one is the y direction. So we call this two mode of motion, and these two mode of motion have to be simulated independently. Okay, so you have to write down the Worley algorithm to involve x, vx, ax. Then you have to write down another Worley algorithm to involve y, vy, and ay. So then you loop the time, then you calculate the position of x and y x1 at different t, then you simulate, and then you want to see with your own eye whether the simulation indeed would mimic a projectile. Then you overlap the projectile that is generated by the Worley algorithm with the theoretical curve. You always know the theoretical curve. We have done that. You know the formula is y is I think equals to x squared, something like that. It's a trajectory for 2D motion is a parabola. Right? So you know the parabola. So you draw a line for the parabola, and then you want to see that indeed all the motions that is simulated by the Worley algorithm shows that yes, all the points are lying on the theoretical line. So that means you know that I have simulated my 2D motion successfully and according to what theoretical predicted. So in the simulations, you always start with known cases, that you know what is a system and what is theoretical solution. So how the solution should look like. This is what you expect. Then you know the theoretical behavior. Then you plot the theoretical line. Then you simulate it. When you simulate it, you just forget about the theory. You just simulate, just put in the force, and then computer will simulate the locations. Then you want to see that indeed your simulations all lies on the theoretical line. Then you know, yes, I'm right. So this is a very important thing that you do in simulations in computational physics. Right? You always have to check that your code output the correct simulations as theoretically predicted. Right, so if you never check your prediction, I got a code that works, it looks like something which is like going around, I'm very happy, but you cannot assure whether it is correct or not, right? So you have to assure people, that assure yourself that your simulation is correct. Only then you will apply it to more complicated cases. So at least your code have to sort of like tally or agree with the simplest case that is theoretically known. For those very complicated one, there might be no way for you to check whether your simulation is agreeing with the theoretical model or not. Maybe there is no theoretical model, or maybe the model is just complicated, right? But at least when it reduces to simple case, your simulation must agree. Okay. So in this example of a Worley algorithm, you just have to specify the force. So you can generalize this very easily, right? So tell me what is the force. So you express the force in terms of A, then you throw it into a Worley algorithm. You just need to change expressions between the force and the accelerations. So for different system, you just change the force. Then you will see different trajectory of object under different forces. So for pendulum force, then you see now the pendulum will oscillate like this. When you change the force to be a two-dimensional projectile motion, then you see the pendulum, then you see the projectile motion like this. And if you apply it to some more complicated case, for example, a Coulomb force, you put a charge there, you fire particles with another charge, a blue color dot and a red color dot. So say the red color dot is the projectile motion, which is flying, and then the blue color dot right here is a fixed charge, such as a proton, and then the red color is an electron. So then when you fire it, these two particles will interact with the force. So you know what is the force looks like. So the force, according to the Coulomb's law, is just this formula, right? It's just KQQ over R square and pointing in the R direction. So you know the forces between them. So in principle, if you know the force, you'll be able to put it into a Woolley algorithm. Then you can simulate the motions. Okay. So if you have a situation where the force is not like KQQ or R squared, but a Lorentz force. What is the Lorentz force looks like? The Lorentz force is F is equals to what? Remember what is the Lorentz force? Lorentz force depends on the charge and also depends on the magnetic field. So I think Q, that is charge, equals the Lorentz force is V, vector V cross B, right? So V cross B is the Lorentz force that describes the charge that is moving with velocity V interacting with magnetic field. So in that case, it's a three-dimensional force, not two-dimensional, three-dimensional. Then the motion would displace the three-dimensional helical motions. Right? So you could also, in principle, do that simulations in 3D. Okay, so that is actually very important, very interesting. So as long as you know the forces, then you can just do the simulation. Okay, now, any questions? Okay, so now let's just try to simulate the force on a pendulum, and then see how we do it. Okay, so this is what we're going to do now. I have already written the Woolley algorithm for you. So this is the 1D pendulum. Okay, so maybe I think it's not that difficult. As usual, I would like to try to reproduce it, at least for the simple case one. Then let me do it one by one. So first of all, you have to do your simulations, and then let me open up a little bit of my PowerPoint here just to refer to this. Okay, so we are going to do this. Let me see. Let me make it slightly smaller. Okay, so I need to show the simulation. So I need a IPython. I need to plot the graph. I need to do the NumPy, and then I need to set the constant. So the constants is K and M, and then once I set the K and M, I think that's what but I need what? I need to know, this is a pendulum system, right? So I need to calculate the period first, right? I'm going to express my time in unit of the period. So what is the period? Period is dependent on the omega, which is the frequency. So frequency is just equals to K over M, right? This is a formula that we have all known, and then omega is raised to the power of 0.5, right? So this is the frequency for a spring with constant K. Omega is proportional to the square root of K. K is the strength of the spring, right? So if the spring is very strong, in this case large, then the oscillations of the spring will be faster, right? So the oscillation frequency is then should be somehow go together with the strength of the spring. That's why the K appears on the top, but instead of M over K, it should be K over M. And if the mass is very large, then the frequency would sort of slow down, right? So that means I explain that M is in the bottom of the expression. So that's how you relate the angular frequency to the spring constant and the mass, and it's raised to the square root. So once you have done that, then the period is just equals to 2 pi. It's equals to 2 pi. So this is pi, 2 pi over omega. So this is the period. Then I have to decide what is my length, what is the length of my simulation time. So I want to do it for one period. That's how I do it. But let's say I want to simulate for a longer period, maybe like 5 periods. Okay, this is my 5 periods. So I'm going to simulate for 5 periods. And then I need to define my delta t, that is the intervals in the time of my simulations, or called time resolution. Then it should be then the total length of time divided by a constant. So the constants T has to be chosen, right? So I have to choose it to be say 100 or 200, whatever. So I just choose it to be 100, just to say at 100. Then I need to have the initial conditions, the initial value 0.1 and 0, and V0 is 0. So I need these two initial conditions as a condition to be placed into x at 0 and x at 1. So then I'm going to, so now in this case, I've already defined all the x0, v0, and delta t. So this on the right hand side, you see on the right hand side, I'm pointing to the PowerPoint. So these three number has been defined. Okay, so now I'm ready to go into a for loop. I see the for loop for n in nt. So it should be range from 0 to n to nt. So that should be the case. Then the time is equals to, well, the time, maybe you don't really need the time, but you need to say the time is equals to n multiplied with delta t. Okay, so that is how you calculate the time. Okay, so then you need to calculate the AX. Right? AX is calculated to be based on the n. Right? So you have to give an index to the n. Now you can also give an index to t if you want, but this is not necessary. But since we already given it, then we just construct AX as an array, and the values of A at index n is just equals to minus k over m multiply with x at time n. Right? So when you go into the n loop, n will begin with 0. So x at 0 has been defined. No, not yet defined. So we didn't know what is x at 0. So you have to define here x at 0 is equals to x0. Right? So that when you calculate ax at n0, then it has a number. Right? The values of ax at 0 is based on x at 0. So if the computer does not know what is x at 0 in the beginning, then it will not know what it is. So you have to assign the value to x at n equals to 0. But then is that a problem? Then there's a problem, because in this case, what you are saying is that I'm going to assign t as an array, ax is as an array. Right? So when you write this a0 in the square bracket, you are assuming that this variable ax are array variable. So you cannot in Python use the array without declaring it. Right? So when you want to use that, then you have to declare. So you say I'm going to call x as an array. So I'm going to generate an 0 array, zeros, and then it's going to generate an array of some dimension. So how many dimensions are there? So I think this should be empty, but maybe it's not empty, it should be empty plus 1. You'll see it later. Anyway, I'm just declaring A as an array which has empty space. Okay, so then I also have to declare t as an array, and then I have to declare Vx as an empty array. Okay. Now, other than that, I also have to declare Ax. Okay. Ax will appear later, and is also an empty array. And then I need to also assign Vx at the beginning to be V0. So this is an initialization situation. Initialization means that I assign the values to the initial velocity and initial positions, and then I also have to initialize the arrays used in my code. So I have how many arrays? I have t, a, x, v. So you have 4 arrays you have to declare. But this is something which is not very nice in Python. In Mathematical, we never need to declare the array. You just use it without declaring it. You have to prepare the array in the beginning. Right? You have to prepare an empty array. So then you have now see this is the second line on the right hand side, ax is equal to minus k. So then we go to the third line. So we're going to do this third line, ax at the next n. So this is how you do it. x at n plus 1. Okay, this is what I'm going to write. X at n plus Vx at n multiply with delta t plus 0.5 multiply with a at n and multiply with delta t square root. So let's check again. X at n plus 1 equals to x at n plus Vx at n multiplied with delta t. That's right. 0.5 a at xn and delta t. So it looks like it's correct. But before I proceed on to the next line, I would think it would be good practice to sort of what I call run it, right? So I run it, but maybe I forgot to save this as a different file name. So let me save it a different file name. File, make a copy so that it won't overlap with the original file. Okay, why is it so long to just rename it? So I just want to rename the file as this one. Okay, so I'm here. Okay, so this is a pendulum. This is the original file. Okay, do it here. Just paste the code that I written down. Okay, so I'm working on this file, which is copy one, which is different than the original file that I shown on my lecture notes. Okay, I'm not going to save it. I just close it in case I accidentally modified it. I don't want to modify the original file. Okay, so this is the code I've written now. And before I proceed on, I just want to make sure that my code is not making any noise. Right? So before you make the calculations to be really complicated, just try to check before you go too far. Okay, so I'm going to press Shift Enter to check if there's error. Okay, there's no error. So it looks like until this stage there's an error. A is not defined. So where A is not defined? So A should be AX, right? So this should be AX. So now I checked it. I press again. Okay, so you still have an error. So index 100 is out of bound for axis 0 with the size. The reason is because when you do that simulation, the X runs from 0 to 1, right? So you look at this one. N is supposed to be in the range from 0 to NT. But when I run this code, I'm going to have an additional space, additional value for x, because x is not only exactly at x at n, but x at n plus 1. So when n runs to the n, the x here actually requires one more space, right? So you have to then increase the dimensions for x to be not 0 to nt, but have nt plus 1. So you would realize that you don't have prepared enough space to accommodate the arrays that appear. So just give more space to array. I think you can add in 100, what does it matter? I think you can add in more array than less. If it's less space, then it will not work. But if you assign more space to the array, then it works. Okay. So let me try to press the button and run again. See if the error goes away. Okay, it looks like there's no more error. So at least at this stage, I'm okay. So I have finished coding the x, the formula for x. So let me now go to code for, say, A for the x. Okay, so now is the next line. So this line and the line here is exactly the same, except that we are going to evaluate ax at n plus 1, and it's going to calculate that value of ax at n plus 1 based on the values of a of x calculated at n plus 1, which is the value that is obtained from the previous steps. So this is quite straightforward. So now we go to the next line. So I think I better cut and paste this one so that I can recycle it. Okay, so I'm going to calculate Vx at 1. It should be then Vx at n plus half. So I have a half here. Okay, so I'm going to throw this away. and this is the half of something times something. Okay, it's a half of ax at n and ax at n plus 1. Right? So this is what is said here. The half of ax plus 1 and then delta t, but it has no square. There's only delta t here. So press the button. There's an error because this is don't not C. This should be the Vx. Okay, it looks like okay. So now this loop seems to be completed. So I have already completed all this. So now it's show time to do the simulations. So I'm going to do the simulations. So the simulation would be, no, I just need this. I need all this stuff which I forget to do the display. I need to do a display. Okay, so that is what I want. So now I will start to do my display. So I'm going to do the displays, then I'm going to plot. So before I go into plot, I'm going to prepare ax dot y. I'm going to prepare a figure, and then I'm going to prepare a axis. And this is defined to be subplot plt dot subplots GLT plot subplots with a bracket. Right, so this is to prepare ax. Then I'm going to plot the graph in ax. Okay, I'm going to plot the graph on ax to say plot. Now plot what? I'm going to plot the positions of x. So this is a bit difficult for me to explain. So you have a point lying along the table. I have a line, a table, and then it's oscillating. So in the one-dimensional motion, you want to display it. So, but in the plot, you can only display the plot on a two-dimensional plane, right? So in this case, the y dimension is considered not changing, only x. So the x coordinate is moving, but the y coordinate is not moving. So in that case, you have to show the point. But how do you show a point? I think show a point is like this. You show a point, and you have to displace the x coordinate and the y coordinate. Right? So the x coordinate is just x, x at n. Right? Then you have another coordinate which is y, and the y coordinate is fixed to be 0 in this case. Okay, so let's see if this is working. I think it may not be working, but anyway, I'm going to show this in the bracket. So this is an array of xn, but the array has only one value. Then this is the coordinate of that array. And then I'm going to show ax plt. I think maybe this is correct. Then let's show. I'll say plt show. Okay, let's see if it works. There's an error. I think because of subplot. I think that is a problem that I'm facing since yesterday. I do not know actually what happened. So it looks like I cannot use the subplot here for some reason. Okay, the reason is because some stupid reasons. Now you see, if I do like that, I cannot use the subplot. Now I challenge you to find out what's the problem. Right? So what's the problem that I'm not allowed to use subplot? You look at the error, say axis subplot subject has no attribute, and then there's error along this line. So we give you a time to look about this. We take a break and we'll come back at 4:10. Okay, then you come back and tell me where is the error. Why is I have this stuck at this error? Okay. Okay, so take a break. Any questions? You are welcome to ask me now. Okay, 4:10. We'll meet again. Okay, continue. Okay, so we resume our recording. Okay, put it here. So the problem with the code is that the naming should be not recycled. It should be different. AX1 is a name for the axis where I display my graphic. So this should be AX1. Okay, so it's called AX. Then I got another error because of what? I have no PLT. Okay, so the axis is AX PLT. Where is the problem again? Equals to this plot subplots. Save it. AX1 plot PLOT, not PLT. Okay, plot show. There's still error. AXY is not defined. So Y is the x-axis, is the y-axis for the pendulum, right? So we assume the pendulum to be lying on the lying flat on the surface. So the y coordinates of the pendulum, which is moving in one direction, is not changing at all. So we fix x, which is y, to be just constantly equals to 0. Okay, so just set y equals to 0 somewhere. Maybe just upstairs here. Say y equals to 0. That's all I need. Okay, so now y is defined. I don't see anything because when I asked you to plot, I did not specify what to plot. So I should say specify a plot of a point as a point like this. Okay, so now I see a point. So I simulate it, run it. I should plot me a point. Now it is waiting for so long. So you see the screen here, it's always waiting for too long. Never mind. Let me try to see. Maybe it's just too much. So let me stop it. Okay, let me stop it and refine it. Restart it again and do all over again. Run. Let me save it. Run. So when I run, it is running and the figure is still running. You see here. So let's wait for a while. But this is not going to work very well because I have not fixed the frame, the axis. So I have to fix the axis. So the axis has to be fixed. So the command line to fix the axis, remember what was that? You have this fixed axis thing, which is where is it? Okay, so maybe I just plot this is a fixed axis. So just set the limit so that the limit is set to be x left, x right, y left, y right. So I have to define my axis value. Okay, so the axis value I have to fix what is the x left and what is the x left, x right. So f left is some number, f right is some number. So this is extreme left, extreme right. So the extreme left should be equals to minus what? It should be minus x0. Right? So because the oscillation has the amplitude of x0, 0.1. So it oscillates between minus 0.1 to plus 0.1. So this is the extreme left and the extreme right. Okay? And then the y low, y high. So y is just the height of the simulation box. So let's just make it to be, say, minus 0. Well, just fix the number, say minus 1. And then this just fix it to be 1. Yeah, I think that should be fine enough. Okay. So let's just run it again. Now you see this is oscillations. It's fixed in x and y. And yes, it's indeed oscillating. So you can do a better job by drawing a line, x and y. So maybe just plot a vertical line on it, but you don't really need that. Now if you want, you can do a spring or this. No, you don't do a spring. Now to make things much better, you just have to increase the simulations, maybe to say 300. Now I expect that when you do that, the simulation will be smoother, right? Instead of just like snapshot and snapshots, it should then display in a smoother manner. I don't really like these Python things. I'm not sure. Maybe it's my technical knowledge is not good enough. Sometimes you just wait for too long when you do the simulations. Okay. See, I think this is the old one. Isn't it? Still waiting. Still waiting. Okay, let me close it and restart it over again and see if it's running faster. Run. Okay, partially. Run again. Now you see the simulation is smoother. Is it really smoother? Yeah, maybe it's smoother. Okay. So if you were to do a better job, I think the existing code that is run here, it looks better. I think it looks better. Where I somehow managed to make this to have a string attached to it, so that you draw a line between the point and the origin. Okay, so you can do a better job to do the simulations by attaching the dot, draw a line between the dot and an origin. Okay, so in this case, you can, now here I have only simulating a moving dot that is changing. Now it is possible to fix the origin and then draw a line between origin and the point. Right? So you draw a line to do that. So how do you do that? So here this is referring to the x coordinate of the pendulum, and then y here refers to the y coordinate of the pendulum. Then what you do is that if you want to draw a line between the point, origin point, and the oscillator, you just have to define the x coordinate of an origin, y coordinate of the origins, then a line will be joined between them. So I think this is what you do. You add in the x coordinate for the origin, and the y coordinate of the origin. I think this will draw you a line between the point, maybe like this, a line between a point, between 2 points, and see whether it works. Hope that I won't need to wait for too long. Save it. I always wait for too long. Okay, I have no patience for this. So maybe I should just stop this, and then clear all the memory again. Restart, reset. Okay, now run again. Okay, so I get something, right? Okay, it looks like I get something. I have this figure, blah blah blah. Okay, kernel is ready. So when I press, I should get the simulation. Right. So I get the simulations. That looks like this. Okay, a line that is drawn between them. Okay, so if you want, you can make a double dot line. With double dot line, then the simulation will be a double dot instead of a continuous dot. Okay. So that is how you do a simulation for a pendulum using Rayleigh algorithm. So now let us proceed to do the simulations for the two-dimensional problem. So it's actually quite easy to generalize or to simulate the code based on to simulate the two-dimensional projectile motions based on the code that we have already written here. It's just that you have to add in the AX and the AY instead of having those on the AX. And in this case, for the two-dimensional pendulum, AX is always 0 here, right? So the AX is always 0, and AY is just a constant of -j. Okay, so let us modify our code here to make it look better. So maybe I just make this larger a little bit. Okay. So how do you do that? So let us try to recycle the code. Okay, let me maybe I just recycle the code from this one. So let me throw away this one, cut it away. Okay, so this is the code I'm going to recycle. Copy. Well, we copy this, everything, almost everything, except the display part. Okay, so I add in a thing, a panel, and then, okay, so let's look at this one. If you want to do a simulation for 2D pendulum, so you don't need this constant thing, right? But you do need what? You do need the gravitational value, 9.81. And then you need to express your period. Now, what is a period? Now, the period for these situations is very similar to what we have studied in the case of a pendulum, right? So if you recall and use the previous code, Now let me recall the previous code for the simulations of the projectile motions. I need to define the t-half, which is the time taken for the pendulum to reach to its maximum height, and then also the range and the height as a scale for me to define my period. Okay, so here I'm looking for the expression for t-half and then also for r and h. So the r would then be used as the sort of like maximum height for my simulations, and the h will be taken as the length of my simulation box. Okay, so I need this number. So what I do is just a cut and paste. Okay, here is just cut and paste. Just cut and paste this thing here, and then I put it back in these situations. Okay, so maybe I just stop this. Okay, just stop this and then throw away all this stuff. Okay, so I'm going to do, where am I? Okay, so I'm going to do this over again from here. Okay, this is the one. So I'm going to cut and paste so that I have the initial positions, the constants of g, velocity, initial velocity, and I have an initial angle of 45 degree. Then I define my t-half, and then I define the t-last to be 2.5 of t-last. And then I don't really need this. Okay, do I need this? Maybe I just keep it. The time is to simulate from between here to here. So maybe nt is a number. So nt is a number that I define to be, say, 50. Okay. Then this is a simulation time. And then I have my initial values for the x coordinate, and initial velocity along the x, and initial velocity along the y. Okay, so then I don't need this. But then I need my delta t. Okay, this is my delta t, which is defined. Then I don't need this. Okay, but I do need the array. This is my array declared for t, x, and blah blah blah, x, t, vx. Okay, so this is the initial conditions which is defined. So this is the initial condition for the x coordinate. Remember, in our two-dimensional motions, we have x and y coordinate. Okay, so not only x, but I have another version for y. So just add in the y conditions, y naught, and then v y at 0. So but you have to be very careful. The Vx is initial velocity for the x component, and it should be V naught x. Okay, it should be just V naught x that is declared to be V naught times cos theta. So this is the initial condition. Vx at time 0 is given by this. Vy at time 0 is then given by Vy naught. Okay, so this is what I'm saying. Okay, my f left should be declared to be r. Okay, so what should my r be? Now my r can be cut and paste from here. So where is my r? My r is the maximum value for this. Okay, so this is my r and x. Okay, so let me show it here. Now let me paste this. Now this x right is just the r naught. Okay, so this is a range, that is the time taken for the x component to travel. So this is, I define my x left, x right, and then y low and y high. This is my y low, which is the lowest point the projectile will reach, and then y high is the maximum height it will reach. So all this, now for example, this y high is just y high, it's just the value that is like this. Okay, so the y high is just this number. Okay, r is just the time taken times whatever. So the r is actually not, well, r is a range, but the values I'm putting here is not the r. Okay, so this is not really the r, but it is the total length of the travel time along the x-axis. Right, so you define what is the leftmost and rightmost box size and the highest and lowest side values of your y. Then you define it here. This will be going in to define the size of your axis, right? So you need this for your plot x limb and plot y limb. Okay, so now I have done this part for my initial condition for x and y. So now I'm going to enter. So I'm going to define my ax. Now what is my ax? Ax is the acceleration. So according to the force that we know, the x on the x component, what is the ax? Ax is always 0, right? So you don't have any number for this. It is 0. Then this line is exactly the same. Right? It doesn't depend on the system. It's just a Boolean algorithm. And then this has to be changed. Like the accelerations at the next moment of time is also the same as 0, because the acceleration at now or at n plus 1 is always equals to 0. And then this does not need to be changed because it's just a Boolean algorithm, doesn't depend. Well, anyway, it just doesn't need to change. So anyway, this is the x component. So now you have to add in the y component. Y component is ay, and then y etc. So let's do it line by line. So what is your ay? Your ay, according to the formula here, the acceleration along the y directions is minus g. Okay, so just put in minus g. Okay, minus g. And then here, this again doesn't need to be changed. A at y. Now let me have to be changed. This is a y. Okay, so it should be y. All the x have to be changed to ay. Okay. Then your ay again is not dependent on positions nor time, so it's still equals to minus g. Right? So this is how you assign the acceleration along the y direction at time n and at time n plus 1. Then this again does not need to be changed. Okay, so now the x and y component has been defined. So what we want is to displace the x coordinate and the y coordinate on the two-dimensional plane. Okay, so now I have to throw away this dy, and then I define my subplots. Then I define my range. Then I decide what to plot. Okay, so what should I plot? Okay, I'm going to plot the ax and y. Okay, I'm going to plot x and y like that. I think that's all I need to do. I hope that it runs. Let me save it and then plot show. I don't have error. Do I have error? Yeah, I have error. The ax0 is not defined. So let me see what's the error. Name y is not defined. Y is not defined. Okay, yeah, it's true. No, not true. Yes, yeah, it's true. Because I am using x, y as an array. So I forgot to declare the array for the y component. Right? So I have array for y. This is not required. Empty has been declared. V for y, and then I also have to have a for y. It's all declared to be an array. So let me press a button. I got another error. So I got an error for ax. Okay, here this is always stupid error. Okay, n. Just typo error. Okay, so it looks like I have this. Flowing. Is this moving in the same way that I expect? No, it isn't. Right? It doesn't look like it's a projectile. Okay, so there's something wrong with my x and y. This is because this should be vy, right? Not vx. So this should be vy, ay, right? So when you look at your result and you know immediately it's wrong, then you know something. If you look at something simulation, if you look at the simulation and you do not tell whether it is right or wrong, that means you are not knowing what you do. So it looks like this. Yeah, okay, it looks good. So let us do a better job by plotting the x-axis and y-axis on it. So I will set PLT A, what is that? AV vertical. Well, I just take a look at this. I forgot. I just plot V. Okay, this V line. Yeah, I think this V line and H line is what I want. So I just plot the V line and H line. Okay, this should be PLT. So I have the reference line, but I need the trajectory. So the trajectory has been actually been shown. So this is a trajectory. So I just define my x and y coordinates. So this is my x and y. Okay, so in order to plot my graph, I just cut and paste this one. This is for decoration purpose, okay, because I want to show the curve. So what I do is that I just add in another section where I define my x, but I cannot define my x here because x has been taken up. So I just call this a, maybe just a, whatever, a x a. Okay, just to show it's a axis. Then after that, then I'm going to cut and paste this one, and then I'm going to show my x array, y array, and then display my array based on this one. So this is an x array, y array, x a, y a. So this array has to be x for t in t array. Okay, I think that is what I need. And then theta has been defined. So this is for x and y, and this is my y, this is my ya. So this will generate an array of ya, where ya is defined to be like this, and I'm going to run t to be in t array, t-a-r-r, like this, and I have to declare my t array. So did I declare my t array? Yeah, this is my t array that I have already declared. So by doing that, then I'm going to say I'm going to plot plt. Well, anyway, this is an array that has been generated. So I'm going to plot this and then plot it into ax1 so that they will all appear in the same thing, in the same place. So ARR, YARR. So that will plot you a trajectory. Let's plot trajectory to be a line like this. Maybe this one should not be like this, just like this. Okay, so let us pause the button. Okay, so now you see this is the trajectory that I plotted, and you see that indeed the trajectory and the simulation given by the Rayleigh algorithm. Right? This is the Rayleigh algorithm. It's displayed on an overlap on the thing. So this is very nice, right? So you learn how to look at the Newton's law, like shown on the screen here. Then you would absorb the Newton law into the Rayleigh algorithm. You have to assign what is your a, x, a, y at different time. So as long as you know what is your a, x, a, y, then you just modify this Rayleigh algorithm expression. You'll be able to do a simulations. Okay. So this is not so challenging. Now let's look at some more challenging questions. So this is your assignment. Okay, so your assignment would be quite terrible. Well, not really terrible. Just challenge you. See, we are towards the end of the course. Right? So what have you done? What have you learned? So now I'm giving you a chance to learn some good physics. So let us look at a scattering projectile motions. But this is not an ordinary projectile motion. This is something which is quite new. We are talking about a Coulomb force. Okay, so let us look at a Coulomb force. Maybe not this one. Let me look at this one. So this is your assignment, right? So I just absorbed this assignment. The last few slides into the assignment. So assignment 12, you're going to do it. Okay, so consider you have a charged particle which is Q. To fix the charge, big Q, like say a proton at some position RQ. So you have to know how to define your locations of RQ and Q. If say Q is say one electron charge or 2 electron charge, whatever. Then you have a smaller charge which is called small q, and both are supposed to be positive, right? So both of them would sort of like expel each other when they get closer. Okay, so you expect that when you have two charges which is moving towards each other, well, one charge is fixed and now is moving towards the other one, then they will have a repulsion between them as they get closer and closer. If they're very far, then it will not close, it will not feel any different. But when they get close, the Coulomb force will act as a repulsion force, and then that repulsion force will change or deflect the projectile of the charge. Right? So this is what you expect. If they are positive negative charge, there will be an attraction force. Right? So then the force, the projectile motion, instead of being reflected away, it will get attracted towards the charge, right? Because there's a attraction force between them. So the force between these two charges, big Q and small q, depend on the relative sign of charges between them. If they are same charge, then there will be repulsive force. If it's an attractive force, then there will be the cause of this trajectory will be different. So you have a mass for the projectile motion, then you have a fixed target Q, big Q, then you fire at the Q. Right? So if Q, if the angle between the trajectory motions and the target is 0, that means you aim exactly at it. Right? So this angle that is shown here is referring to the angle between the line of this Q and Q and the directions of the motions of the small q. But if the angle between the velocity of the small projectile Q and the line joining the big Q and small q is 0, that means that small q is hitting directly into that thing. So this is what I'm talking about. So the angle here between the red color line and this line. Okay, so this is the velocity. This is the RQ is fixed. So you are shooting this red color thing, right? So you shoot it along these directions. Then the angle is defined to be like this. Right? It's defined to be the angle between the origin positions of the projectile, and this is a fixed target. Right? So in this case, this angle is like maybe like 20 degree or 30 degree. But if this angle is like 0, that means the projectile is facing directly towards the motions, towards the target. Right. So when you do a simulations, you first decide how far is your projectile motion from the origin and the fixed target. Then you decide what is the angle of the velocity by the projectile motions. So you fix that 30 degree, 10 degree, minus 20 degree, or you cannot make it to be, say, more than 90 degree. Make it to be, say, 180 degree. Because in that case, that the projectile motion will not be shooting towards the target, it will be away from the target. Then you won't see any difference. Right? So you should shoot the target, shoot the projectile at an angle which is close to 0, say 10 degree or 5 degree. If you shoot it at 0, that means you are shooting it directly. So you have this angle that you can play with when you do a simulation. And you have to provide an initial speed, like a V0. So your simulation will have to say, assume how far is your target away from the initial position of the projectile motion, what is the initial speed of the projectile motion, and what is the initial angle of your projectile motion. Initial angle here means the directions of this velocity with respect to the line joining the original charge and the target charge, okay, initially. So then you know at any instant of time, the force between the projectile motions and the fixed target is given by the law of Coulombic force. Right? So any instant of time, the charge have a coordinate of RQ, which is spin up of x and y. So x and y refers to the coordinate of the positions for this projectile motion, and then the charge Q, big Q, is fixed. X, big Q, y, big Q is fixed. So you know instantaneously the distance between these two, which is a big R. So then the distance is given by this vector formula. Okay, so you just look at this one, you just calculate the vector between them, then the magnitude between this point and this point at any instant of time is known to be R squared. So you can calculate R squared quite easily if you know the instantaneous coordinate x and y and the fixed coordinate xq and yq. So you know the forces, that you know the force x on the projectile motion. So this would then translate into the AX and AY. So this is the positions of small q, big Q. Then the force, and the force is resolved into the y component and x component. The force resolved into y component give you AY, and the force resolved into x component gives you AX. So you know the expression for AX and AY. Okay, so this is the AX and AY. So now your job is to do the simulation. So you know the force, and you throw the force into your the expressions of your Valais algorithm. right? So you throw them into here. So basically you look at the AX, so just modify your AX, then you modify your AY according to the Coulombic force. All the formulas are given to you. Then you just do the simulations. And if you do the simulation nicely, this is what you see. So this is the old simulations. Okay? These simulations that is taken from the Mathematica, but your Python may not be able to reproduce this. And so here, my Mathematica actually allows me to change the initial speed, the initial coordinates of my projectile motions, an angle that I'm going to shoot, and the locations of the target. So I think this theta 2 refers to the angle, which is 30 degrees from the origins, and then this time steps. So I'm shooting a charge, which is in blue color, into the thing. Then you see that you can actually shoot a trajectory shown point by point, and then you can see that it deflects because you have the same charge. Now, if you change the angle to be, say, closer, to be 30 degrees. See, this 30 refers to the angle between this point and this point. So I think it's something like 30 degrees. So if I fix my projectile motion to be 30 degrees, I make these two numbers, theta and theta to be the same. That means it's directly hitting towards the center. Then you can see that it reflects. If you make this angle to be largely different, say you make the theta 1 to be like, say, 20 degrees, which is like going like this, then you will see its deflection will be lessened. So you can actually simulate the trajectory of the motions using this very simple method. Okay, very simple simulations. So you can play with this. You change the angle, then you change the velocity, then you'll be able to track and displace the trajectory of the projectile, which is a charge towards another charge. Okay, so I think last 2 years, people use this as a method to perform what we call Rutherford scattering. You know what's Rutherford scattering? Rutherford scattering means that you have a nucleus made up of gold. Then you assume that the nucleus has certain distributions of positive charge within the atom. Then you fire an alpha particles, which is a small charge, and then you simulate the trajectory of alpha particles towards the gold atom. So you assume the charge will be distributed either at the point inside the atom or distributed evenly throughout the whole atom. So then the trajectory of the alpha particles, when it's hit towards the model nucleus, then it will show different trajectory. So if the charge distributed inside the Rutherford atom has a different distribution, say the distribution could be all concentrated on the nucleus, or the charge could be concentrated on the whole atom. The different type of charge distribution inside the Rutherford atom will cause different trajectory. Right, so you can actually simulate that kind of simulation as though you are performing the Rutherford scattering. You know what Rutherford scattering? No, you may have forgotten, then you will recall your 104. ZCE 104, you have a chapter on Rutherford atom, right? So you study that Rutherford in the earlier days, 1920 or something like that, uses alpha particles to shoot on a very thin foil and find alpha particles to be recoiled back. So from there, you got a Nobel Prize or something like that. No, I think the Nobel Prize for Rutherford is not for that, but establish the fact that the charge in the atom are all concentrated in the nucleus. So in that day, they perform the simulations of alpha particles as a projectile shoot directly into the gold foil to reduce the distribution of charge inside the atom. Therefore, then you deduce that you have this Rutherford atom, all the charge is not distributed evenly on the atom but in the nucleus. So that was achieved using experimental method. However, in this simulation, you can just simulate the whole Rutherford experiment. Like, for example, you can simulate one trajectory, two trajectory, each trajectory to be simulated with different angle, different initial position, different flux. So you can simulate this many times of, say, millions and millions of trajectory motions. Then you collect all the trajectory. Then from that trajectory, let's say you have simulated, let's say, 1,000 different trajectory hitting the nucleus, and each time the nucleus have different distribution of charge. Then you will be able to track out what we call the cross-sectional area of the process, meaning that you have a projectile trajectory, many projectile trajectory, and you assume some model of charge distribution. So different charge cross distribution will give rise to different trajectories. So you calculate the average behaviors of this trajectory, then you come up with a number called the cross section, or differential cross section. So then this differential cross section tells you how the charge in the atoms is distributed. So you change the cross sections. Well, no, you don't. You change the charge distribution inside atom, then you have different differential cross section. Then the shape of the differential cross section will tells you what is the distribution of charge inside atoms. So you carry out experiment, you got this cross distribution, you got this distribution cross section. Then from there you infer the distribution of charge. So this is physics, right? You perform experiments, then you do a modeling, then you compare your experiments with the model, then you decide, oh, these experiment results have this shape, and my model has many different shapes. For one particular distribution, the shape predicted by the simulation and the shape that you experimentally measured agrees. Therefore, you said the models of the charge is based on my simulation to be like this. Okay, so that is how you perform a hybrid kind of test. So you carry out experiment, you carry out simulation, you compare them, then you decide what is the model that explains your experiment data. You know, black hole, people find black holes, not black holes. People find gravitational wave these days, and 2 years ago people used a gravitational wave. Gravitational wave is very important and got Nobel Prize after 1 or 2 years of discovery. So then, now the way how they obtain the gravitational wave is through this method. So in general theory of relativity, they have all the formulas. So they assume different type of black holes merger, and different merger would give rise to different patterns of gravitational wave mode. Right? So they simulate different black holes merger. You know, maybe like one is larger and smaller, one with this kind of radius, one with that kind of radius. So different types of arrangement in black holes will have different mode of oscillations. So they have all these simulation done in the computer. So then what they do is they go to the sky, they scan the sky. No, they don't scan the sky, okay? They detect the gravitational wave using this long arm in the whole world. So what they do is that they detect the vibrational modes that is collected by the LIGO experiments, right? So the LIGO experiments are very sensitive. So they measure these LIGO vibrations, and then from the vibrations, they compare the vibrational pattern with their simulations. Then they will pick up those simulations that predicts the vibrational mode that match with the experiment. Therefore, they know that this vibration that they measure from the lab is coming from black holes with how many size of, how many times the size of the sun merged with whatever another black hole with what size of sun. So this is a typical example, a classical example of using simulations to do physics. Okay, so you are learning this stuff. So I'm going to give you this very simple exercise. It's a simple one. Last time we used to simulate a helical coil in 3D. But this time I don't give you this exercise because it might be too difficult for you. But in principle, if you have a electric charge moving in a magnetic field, not a static electric field like in this case, you can actually simulate a helical coil. You can simulate a helical coil of electron particles moving in a magnetic field. Then you can play around with the design of the magnetic field. So you can have a uniform magnetic field, then you see how the coil looks like. If you have a magnetic field which is like concentrated in the middle and then weak towards the end, then you have this magnetic bottle. Then you can see that the charged particles will be like bouncing between two walls. So that is how people use it to simulate plasma capture. We have these nuclear fusions. We have nucleus fused together to perform free energy in the nuclear fusion. So you have to simulate how charged particles move in this plasma under a very strong magnetic field. So you can simulate that using similar method. As long as you know what is a magnetic field, then you can simulate how charge are being captured inside a vacuum or inside some limited amount of space. You can squeeze the space by changing the magnetic field. So this is a very powerful method in physics. Okay. So that's all I want to tell you about these simulations. So I'm running out of topic. Maybe if I were to either continue with this lecture or if I find more topics. If not, maybe we'll just have to stop somewhere, maybe next week. So maybe next week will be one of the last lectures. So I have to figure out what to do. Maybe your lecture has been back for too long. So we are ending the course. Maybe next week or the week after next will be your test. Right? We have said that we're going to have a test. So sometime we're going to have a test. Okay, so maybe next week. Okay. So next week Friday. Next week Friday we're going to have a test. And then next week Tuesday will be lectures as usual. But now what topic will be tested on? I'm not decided yet. Maybe on simulations or maybe on something else. So I'm going to ask you for I think 1 or 2 hours of test simulation on a test. So be prepared for that. And then in order to pass this test, you just do the assignment. If you can do the assignment yourself, then there should be no reason you cannot score in your test. Okay. So any questions you want to ask me? Next week, Friday, we're going to have a test for 2 hours as usual. Okay. Are you okay with that? Okay, so no one wants to ask anything, then we just stop our lecture here. Okay, so thank you for your attendance. Hope that you are fine and you are doing well. Okay. Okay, thank you.